So hi everyone. It's a real pleasure to be able to introduce Gabriela Sato-Polito. So Gabriela is visiting us actually all the way through Wednesday. So if you want to speak to her, please sign yourself up to on her schedule. If you don't have access to the schedule, just email me and I will send you the link. And Gabriela did her undergraduate in Brazil, and she came to the US to work with Mark Minkowski at Johns Hopkins University and is now an NSF fellow at the Institute for Study in Princeton. She works on gravitational waves that we're going to hear about, but she also works on density mapping and other things. So she has lots of things to talk about. You should please sign up with her while she's here. Don't miss this opportunity. And please take it away.
Great. Yeah, thank you so much. Really happy to be here. Yeah, I'm going to talk about pulsar timing arrays as a new technique to measure gravitational waves, particularly in this low frequency regime. So just to get started, some of the most important observational developments of the last decade have been the first detections of gravitational waves, first measured indirectly through the orbital decay of a binary pulsar, shown over here on the left, to lose energy in accordance to what you would expect from gravitational radiation, predicted by GR, and then directly, exactly 10 years ago, with ground-based interferometers. So this is just the landmark results from the LIGO collaboration with the two measured strains from the two interferometers shown overplotted over there. And the way that this basically works is through interferometers. So this is showing a laser here being split, bouncing off of mirrors, and then recombining. And the idea is that in the presence of a gravitational wave, this will change the light travel time between these perpendicular arms. And so when they recombine here, you will see an interference pattern that can be detected. And the gravitational wave that you measure is basically proportional to this relative change in length of your perpendicular arms. And these types of interferometer measurements, LIGO in particular, sits all the way over here. So this is showing the characteristic strain of a gravitational wave as a function of frequency. And these ground-based interferometers are sensitive to these frequencies of roughly, tens of hertz to tens of kilohertz. So all the way here on the right. And we're sort of living through this interesting time of seeing gravitational waves through a larger frequency range. And so we're seeing this become a reality now. So further to the left here at slightly lower frequencies, there's this space-based interferometer, LISA. And all the way to the left are the gravitational wave measurements by pulsar timing arrays. So these are the lowest frequency gravitational waves produced from direct observations like these that we can hope to measure. And one sort of one regime where this type of measurement is having a really significant impact is in understanding compact sources in the universe. So in particular, the frequency of the gravitational wave that you measure is roughly inversely proportional to the mass. And so while these ground-based interferometers are basically probing compact sources on the scale of a stellar mass, when you go into this regime, you're measuring supermassive black holes, presumably. So the lower the frequency, the higher the mass that you're sensitive to. And in this intermediate regime that LISA is probing, presumably you're catching these objects in between that are very, poorly understood. But so the topic of this talk are these very low frequency gravitational waves that we found first evidence for these sources about 2 years ago. So this is the scientific result that I'll be mostly focusing on. This is a result from one of the collaborations that does these types of measurements in North America in particular. So this is from the NanoGrav collaboration. And I'll basically be talking about what this is. This is a popular news article on the topics saying from the Washington Post, saying in a major discovery, scientists say that space-time churns like a choppy sea. So I'll sort of talk about what this means. Unlike the popular news article, the scientific community is not calling this a discovery yet because it's not at the level of 5 sigma that is required for such a claim, but is strong initial evidence at like a 4 sigma level. So how does this whole thing work? The way that this type of measurement basically operates is through very precise measurements of pulsars. So pulsars are these spinning neutron stars. Let me just play this again. So the idea is that you have these stars that have these jets and they rotate with a very stable period. And every time this beam faces the observer, you see a little blip, right? And these objects are very stable and they can be measured very precisely. And so you can basically use them as these very stable clocks that we see spread across the galaxy. This is just a table of a particular one of these objects taken from one of these observational papers of cataloging pulsars. And this is just showing some of the quantities that are measured. So this is, for example, the spin frequency. I've highlighted a few here, but this is the spin frequency of this object and the rate at which it spins down. And these decimal places are really measured. These measurements are very precise. Might look like a mistake by someone who doesn't know how significant figures work, but these are actually measured to this precision.
No more.
Okay. And the precision with which these pulses are measured is given basically by this number over here. So roughly 100 nanohertz or so is the precision that you can determine these arrival times. So these are basically very stable clocks that we can use. This is just another sort of, maybe this is more of a historical note, but these clocks are very precise, and they're so precise that they have at times rivaled atomic clock stabilities, particularly in longer spans of time in which they're observed. So this is from 87, but this paper is titled "Millisecond Pulsars Rival Best Atomic Clock Stabilities." This is a bit more recent paper studying the usage of X-ray emission from pulsars for like space-based navigation. And this is showing just the stability of the clocks over certain timescales, where these other numbers here are being compared with the atomic clocks are pulsars. So they're really very precise to the point that you can try to use them to detect gravitational waves. And the idea then is that you have these pulsars spread out across the galaxy. Each of them works as a clock. And you're taking measurements of the ticks of your clock. And the idea is that in the presence of a gravitational wave, these will perturb the arrival time of your pulses, and you will see a deviation from your expected tick rate of your clock. Again, here, basically the strain that you can that you're sensitive to is roughly proportional to this relative change in the time over your total observing time. In the slide with the table, we basically saw that the precision with which you can determine the arrival time of your pulse is roughly 100 nanoseconds. And the total amount of time that these objects have been measured at this point is on the scale of a decade, which gives you a sensitivity to a strain of around 10 to the minus 15. And this is more or less the regime that we're in right now. So this is why these things are possible now, because you've achieved a sensitivity that is astrophysically relevant. So to be a little bit more precise, if you imagine that we have we're an observer here on Earth, observing pulsars at some direction p hat, you can define this quantity, the redshift, the relative change in the period of the pulsar that you observe. And this is basically given by the metric perturbation on Earth, so the metric perturbation here at the observer, minus the metric perturbation at the pulsar. So you're always sensitive to this difference in the metric between your two and your baseline. and projected along this Earth pulsar axis. So this term here is basically a geometric factor that tells you the response of your detector to the passage of a gravitational wave, but it's basically just geometrical. It only depends on the direction of your pulsar relative to the direction of the incoming gravitational wave. So if I, instead of describing this with words, this is a plot of what this redshift map would look like. So this is basically a map where every point corresponds to the redshift that you would observe in your pulsar if you had a pulsar at that location. So here I put a source in this point over here. Everything that's in red here correspond to places where you would see your clocks running slow. And everywhere that is in blue are places where you would see your clock running faster. So this is basically what a source looks like in this redshift map of your pulsars. In the case where this is an individual source, you might want to describe this map, for example, by some set of intrinsic and extrinsic parameters of your source. So for example, for an astrophysical source, this would be, say, in terms of the mass, the distance, and so forth that characterize your signal. So in the next slide, I'm going to show basically what happens when you put different sources in different locations of this map, right? So the number over here on the top will be the number of sources. I made it such that each source is equally bright. And I'm going to play this. You're going to see different sources popping up on this map. And you're seeing basically the central limit theorem in action. And by the end, when you have many sources, you have a Gaussian random field. And this is what people call a stochastic background. It's just the superposition of many sources. And this can characterize either, many unresolved astrophysical sources or some, say, primordial cosmological background. This is how you would describe this map. And the idea is to then describe this map statistically, not in terms of the properties of the individual sources that made up this map, but the statistical properties of the map itself. And since you're adding a bunch of plane waves, the mean is 0, but it has a non-zero correlation between different timing residuals in different locations in the sky. And basically what this angular correlation looks like is you have an angular correlation that is given by this curve over here. This is often called the Hellings and Downs curve. And this basically tells you the correlation. We have timing residuals separated by some angle gamma. So, looking at angles, if your pulsars, this basically looks like a quadruple pattern. And the amplitude of this correlation basically tells you about the energy spectrum of the sources that produced your gravitational wave background. So this angular correlation just follows from this geometric pattern that your pulsars, that determines the response of your pulsars to the passage of a gravitational wave. So this is a geometric quantity that just follows from GR. Whereas this amplitude is really determined by the properties of your sources. Another way, just added an additional, this additional picture. Maybe some of you will find this more intuitive, but one way to think about this is to decompose it into spherical harmonics. For this map of an individual source, if you take your coordinate system and you rotate it such that the source is located along the z-axis, you find that the spherical harmonic decomposition of this map basically only has plus or minus 2m, which is a consequence of the spin-2 nature of gravitational waves. But you basically have this falling hierarchy of L's, essentially, and it's dominated by the quadruple term. Once you produce your Gaussian random field map, you're just adding these together. So this follows the same hierarchy, but these are now drawn from a Gaussian, basically. So this is another way, and this is the equivalent in harmonic space of the Hellings and Downs curve that I had shown before. Okay. So there are several experiments trying to look for this signal. So this quadrupolar shape of this angular correlation is sort of the characteristic signal that what produced this redshift in your pulsars was gravitational waves and not something else. Other things will not produce the same signal. And there are a number of experiments looking for these. So these are various radio telescopes that time pulsars around the world. So a few major ones are the European and the Indian PTAs that combined their data sets in the last data release. The Nanograv in North America, which has a few telescopes in the US and in Canada, and then Parkes in Australia. Since this plot was made, so this is exactly showing the number of pulsars that are timed by each collaboration. And then these numbers are the pulsars that are just timed by each collaboration alone. And then the Venn diagram of like pulsars that are timed by simultaneously by the different collaborations. So you have all options over here. This is just to give a sense of like the number of pulsars that are the legs of your detector that are currently being measured. Since this was made, there are a few new developments like Meerkat and FAST are two radio telescopes that have since then had results and have agreed to combine their data sets with the others. So there's this international collaboration called IPTA that will combine all of these data sets for joint analysis that will include these other two that I mentioned as well. So okay, this is the experimental landscape for the field. And 2 years ago, this first evidence was announced for, the first evidence for gravitational waves in this regime. So this is the result that I had mentioned in the beginning of the talk of measurement of this angular correlation in the, your arrival time of pulses and an overall spectrum that sets the amplitude of these correlations. So as a function of frequency over here. So like I mentioned before, the fact that you observe these angular correlations means that the thing that produced your timing residual is most likely gravitational waves. And this energy spectrum is telling you something about the energy density in gravitational waves in each frequency. So this is what I'll spend most of the talk discussing for the rest of the talk. And the sort of motivating question is, what produced these gravitational waves? What are we learning from these observations? And in particular, I'll talk about this in the context of supermassive black holes, which are the most likely candidates of these gravitational waves, and all of the things that we already know about these sources. So basically, what did we learn from these current observations? And one thing we'll try to answer is, how do we characterize these sources, and how does this fit in with our existing body of knowledge and other observations of supermassive black holes in our picture for their evolution. And if people have questions, please feel free to ask them during the talk as well. Okay. Yeah.
So for the also just to display my ignorance, for your Venn diagram, is that number of pulses just limited by how many observations we have, or by how many pulsars there are in the sky that we can use?
Yeah, it's mostly limited by the amount of time that you can dedicate to these types of observations. You have a limited amount of time, and there are some pulsars that are already studied and are very stable. Yeah, so it's mostly the amount of time that telescopes can dedicate to it.
I have a question. What is the physical origin for the curve, the Helling's, this curve?
Yeah, it just comes from the response of gravitational waves. So it basically comes from computing how the arrival time of your pulses is altered by the presence of a gravitational wave. So when you're looking at this correlation, the correlation that you predict will just depend on how your pulses respond to the passage of a gravitational wave.
You have to standardize your pulsars like supernovae, or can you just use them as the curve? Is there any
In terms of their intensity?
calibration, any for observation systematics?
Yeah, I mean, so your pulsars, there are many steps between, your raw data of a pulsar and you actually being able to time them. I don't know if an analogy with supernovae is really the place to go, but I mean, okay, you're looking at a pulsar. They're typically very faint. You need to, for example, stack a bunch of pulses for you to have a profile. So there is, for example, that's a way in which pulsars need to be standardized. You need to actually measure these pulse profiles. And yeah, so I mean, you have these observations. You need to time them for a very long amount of time, have these templates for their shapes, and infer a bunch of parameters for the motion of the pulsar, if it's in a binary, its propagation through the ISM. There are a lot of observational steps between.
Thinking about systematics in the measurement, I'm curious if we have to think at all about our state of knowledge of the local ISM and the distribution of diffuse material in the solar system.
Yeah, that's definitely a part of it. That's definitely a part of it. It's typically not, it's not expected to produce an angular pattern that is quadrupolar between the correlation of your pulses, but it's certainly a noise contribution that is fit in the noise models of these objects. Yeah. Okay. Cool. Right. So coming back to our what produced our sources. So the PTA frequency band, like I mentioned, is in this lowest frequency regime. What sets the range of frequencies that you're sensitive to are basically at the lowest end, the inverse of your observing time, and at the highest end, the cadence with which you go back and revisit your pulsars and do these measurements where you measure the profiles and so forth. So this is what sets the range of frequencies that you can access over here. And in terms of sources, really the only astrophysical source that is relevant are supermassive black holes. So just to give a physical sense of the scales and what's going on, so this is just a diagram of the scales of your detector. So your pulsars are all in the galaxy. They're typically like kiloparsecs away. The sources that you expect to be seeing are supermassive black holes that will be at some, say, cosmological distance. And the frequency, the gravitational frequency that they produce is twice the orbital frequency. And if you just plug in some representative numbers into Kepler's law, you'll see that a roughly 10 to the 9 solar mass black hole at some subparsec orbital separation will be producing tens of nanohertz frequencies, gravitational wave frequencies. So this is the typical system that will be relevant for this regime of gravitational waves. So I think one important difference between the answering questions about this population in this nanohertz frequency range and say in LIGO, for example, is that we actually know a lot about the remnant population of these sources. Black holes are notoriously difficult to measure, but these black holes live in the biggest, brightest galaxies in the universe. And we actually have a lot of other observations of these sources that it makes sense for us to think about when we're trying to understand these sources. So some of the things that we already know about these supermassive black holes include, in the very nearest cases, some very exquisite measurements of, for example, the Event Horizon Telescope and of our central galaxy. Here I'm just showing a little diagram of like where in the universe these observations are made. These are basically where we are in this scheme over here. A little bit further away, we can infer the presence of supermassive black holes in the center of local galaxies directly. So basically every sufficiently large galaxy appears to have a supermassive black hole at its center. And you can infer its presence by looking at the bulk motion of stars in the centers of galaxies. So around, say, within 100 megaparsecs or so, you can infer their masses dynamically, basically from gas or stellar kinematics. And there are these known relations between the properties of the galaxy. Essentially, here this is showing the velocity dispersion of the galaxy, but basically any property that is vaguely related to the mass of the galaxy will be correlated with the mass of the central black hole. And they form these sort of tight relations that are known and motivate studies of galaxy evolution and the coevolution between galaxies and the central black holes. A little bit further away, we're limited to studying black holes that are in this process of accreting. So we're limited to seeing, quasars that form the brightest objects in the universe. And one sort of simple way to think about what quasars can tell you about supermassive black holes is through this so-called Sultan argument, which is just an energy conservation argument. So if you imagine that quasars are powered by accretion onto a black hole, there's just some amount of gas that is falling in and radiates as it's being accreted, then you can have a direct relation between the luminosity of the quasar and the mass that fell into the black hole, modulo this radiative efficiency factor. So if you measure the quasar luminosity function at all redshifts and you integrate, this basically tells you the mass density that was accumulated into black holes. It's just an energy conservation argument. And from gravitational waves, you're of course seeing black holes that are in the process of merging. And so this is showing kind of the standard picture of the formation of binary supermassive black holes, and then down here the corresponding strain. So the idea is that because basically every galaxy that we look at seems to have a black hole at its center, galaxies merge, you might expect the central supermassive black holes to merge as well. And they follow through, so I mean, the galaxy merges, the black holes have to sink to their center until they become dominated by, through some fairly unknown process, until they achieve small enough separations that their orbital dynamics is dominated by gravitational radiation, and they eventually coalesce. So in something like LIGO, for example, you're observing objects that are in this during merger. In pulsar timing arrays, you're catching them a little bit earlier on. So they're in this earlier stage of inspiral. They're basically emitting monochromatically. They're very slow in this very early inspiral regime. And so this is the point where you expect to be catching them with PTAs. Okay. So coming back to our observations, this is basically the information where this information is contained, right? It's in the energy spectrum of your gravitational waves. And the way, so we would like to have a way to model this energy spectrum so that we can compare it to our observations, right? And the way to basically think about it is that this energy spectrum is basically equivalent to this energy density and gravitational wave per log frequency. And if you want to model this, you can basically compute this as the energy emitted per log frequency of a given source integrated over all of the binaries that are merging in the universe. So this is just the energy spectrum that they produce integrated over all of your sources. And this energy that is emitted is essentially determined by the fact that you're in this regime where you're dominated by gravitational radiation. Right? So you expect the dynamics of your binary to just be dictated by the fact that it's emitting gravitational waves, and that shrinks the binary, and that's what makes your system merge. And this fully determines what the slope of this energy spectrum should be. So this is not a case of like astrophysicists liking power laws. It's really a prediction that it really should be this if it's dominated by gravitational radiation. So really, most of your uncertainty just comes in this amplitude of what this spectrum should be. In terms of predicting what your signal should look like, your uncertainty really is just what this amplitude is. Okay, so there are many ways to approach predicting what this number of merging binaries should be. And it's fairly easy to complicate this problem, but one thing to keep in mind, and the approach that we took in these papers that I'll talk about, is to really understand what quantities can actually be measured by the data, particularly given that the data is, a few points in something that is mostly described by a power law. You don't want to throw, 10 free parameters at this problem. So I'll describe how we approach this. I'll basically break down this signal into these two parts. One is this amplitude of your spectrum. And I'll talk about how there's really a simple prediction, and in particular, a robust upper limit for what the amplitude of this gravitational wave background can actually be, given observations of the abundance of black holes today. So if you know what the abundance of single supermassive black holes are just today at redshift 0, there's an upper limit for the gravitational wave spectrum that you should see with these observations. So I'll talk about how we get here. And the second thing I'll talk about are spectral features, so variations in the spectrum that can occur from the fact that your sources are discrete. There's some Poisson fluctuations in their number, and this will produce a signature in your spectrum that you can model statistically. Okay. So coming back, I guess I should mention, the gravitational wave energy density and the characteristic strain square are just related to each other over here. So I'm going to move on to writing this as a characteristic strain square. And the basic step in predicting what this gravitational wave amplitude should be, and in particular what this upper limit should be, is to realize that the single supermassive black holes that exist in our universe today over here at redshift 0 that we can infer, can just observe, are potentially remnants of previous mergers, right? So I can say, suppose that all black holes that exist today have merged exactly once in the history of the universe. Let's pretend like that's true. Then the number of black holes, the mass function of black holes today is just equal to the mass distribution of binaries at some past redshift as a function of their total mass, right? So if they merge exactly once, then this mass spectrum is exactly the same. Where I still need to assume some redshift distribution for this to have happened, but there's a direct relation between these two things. So I can rewrite this prediction for my characteristic strain in terms of an average over redshift, an average over the mass ratio, and here explicitly an average over the mass function. And if you compute this, it turns out that it goes like the mass, it's weighed by mass to the 5/3. So here I'm writing this explicitly in terms of this mass function of sources of black holes today. If I plot this kernel, this is shown over here. Because it's weighed very heavily by mass to the 5/3, you don't even really need to know you don't even need to know about all of the masses of like lower mass black holes. For example, you don't really care about what your small black holes are doing. You're really just sensitive to a fairly narrow range of black hole masses that is pretty high. So it's really heavily weighed by the most massive black holes in the universe. And this mass at which this peaks, I'm going to call this peak mass. This is the most important mass that determines your signal. I said before that we assume that all black holes merge once in the history of the universe. And you could ask, you know, obviously if they merge more times, you produce more gravitational waves. So how much can this change your prediction? So you can consider this merger tree of your black holes. But again, because you're so heavily weighed by mass, as you break them into smaller and smaller masses, they contribute less and less. And you can write this as a series, and you can take the limit where the number of mergers goes to infinity. And it turns out that this converges to a pretty small number. So here I just split them in two, as if every black hole in the universe had undergone an equal mass merger. And it turns out that the difference between one merger and an infinite number of mergers is 60% in your characteristic strain. So this prediction is very insensitive to the actual details of your merger history of your supermassive black holes. You really just depend on more or less just the abundance of the single black holes of the remnant population today. Okay, so now you can pose your prediction in terms of this single number of black holes today, which is a directly measurable quantity. You can look at these scaling relations between galaxy properties and black hole masses. You can compute a mass function for that galaxy property, and you can combine these to produce a black hole mass function prediction. So this is, you can obtain a prediction for the mass function by doing this. And here I'm just plugging in some numbers. So I've expressed the dependence on the mass function in terms of just some abundance here and some peak mass that contributes. So that mass that was the most important mass that I mentioned. Crucially, these are determined observationally, whereas your averages over redshift and over the mass ratio have a maximum, right? If all of your sources are at redshift 0, and if your mass ratio is 1, this will produce the largest possible prediction for your gravitational wave background. And so there's always an upper limit. If you know what the mass function is today, you always know what the upper limit for your gravitational wave background can be. And one thing that we pointed out in this paper is that, so you can go ahead and do this. You can take all of these measurements of black hole mass functions. So this plot here on the left is showing different mass functions based on measurements from different groups. And this is showing the characteristic strain that you would predict by doing this calculation that I just mentioned. Curiously, these points are all, so every curve in this plot corresponds to one point over here at a particular frequency of your characteristic strain. These are the points that were measured by the pulsar timing array collaborations. Curiously, even though these are supposed to be an upper limit, they're a bit lower than what was actually measured, which is what we pointed out in this work, which is a bit strange. If you wanted to phrase this discrepancy in terms of a number of black holes, like an abundance, you just boosted your, say, mass function amplitude by a certain factor, a factor of 2 to 3 in the characteristic strain corresponds to a factor of 4 to 10 in your number of black holes. If you wanted to pose this in terms of these scaling relations that I showed before, so this is showing, again, each point here is a galaxy that has been measured, that has a velocity dispersion and a black hole mass measured. So these points are data. If you wanted to pose this discrepancy in terms of this measurement, you would require there to be galaxies in these contours that are shown over here. So you would have to populate the regions of these plots. Now, there's no reason why you wouldn't have seen these objects. There's no reason why you wouldn't have seen one of these galaxies. They're, like I mentioned before, the biggest, brightest galaxies in the universe. They should have been seen. So this is something we thought was curious about these recent results. In a subsequent paper, we looked a little bit at some observational systematics in determining these mass functions. But I think there is, at the moment, not an easy answer as to why these two things disagree. It's a very new measurement, so there's definitely room in the PTA side for things to be off as well. But I think it behooves us to make this comparison, right? You have a very simple theoretical prediction for what your signal should be. And I think it's pretty interesting when it isn't satisfied. So I'm going to switch gears a little bit to talk about the spectrum, fluctuations in the spectrum. There aren't any questions about this. Okay. So we've been talking about this amplitude of the gravitational wave background. But presumably, if your gravitational wave background is produced by these discrete sources, by supermassive black holes, there will be fluctuations in the number of sources that produce your background. So this is the actual observation. This is what you would predict from a model. So for example, if I have some probability distribution for you'll have some probability distribution of observing a certain number of sources in each frequency bin. The mean is this power law that I talked about before. If you had the cosmic average number density, you would just see this overall mean. But in a given realization of your sky, you see one realization of your sky, you'll have fluctuations in these number of sources. So this blue histogram is one realization of the sky. And you see fluctuations here. For example, these stars correspond to the brightest source in each frequency. Like I mentioned, they're all monochromatic emitters, right? So each frequency bin is just some sum of sources. And you can see fluctuations here based on the fact that you might have, say, some nearby source that is brighter than the rest. And you also see this drop off in the median. So there are basically these two effects that happen when your sources are discrete that you can hope to search for in your observations, which are these frequency to frequency fluctuations and the drop off of your median. So this falls off below the mean generally. Okay, so ideally, then, the way you want to take these into account is by appropriately modeling this probability distribution of seeing a certain characteristic strain in each of these bins, given some model for your population. Okay, so that's what we're going to do. So the idea is that in each of these frequency bins, the total strain that you observe is just the sum of the strain of each individual source that contributes. And each of these individual sources are drawn from the equivalent of a luminosity function. So here you could describe this as the number of sources with a given mass, redshift, mass ratio. But you can compress this into a one-dimensional quantity, which is just the number of sources per strain brightness, right? So it's just an analogous of a number of sources per flux, say in a electromagnetic observation. And this quantity characterizes all of the properties of the gravitational wave background that you could want to predict. So the mean number of sources is just an integral over this. This mean spectrum that I mentioned is just this first moment. Your spatial fluctuations from like shot noise, for example, corresponds to the second moment. So this contains all of the information about your sources. And a useful number to keep in mind that will determine how important these effects are is this characteristic number of sources that I defined over here. So you can define this characteristic number as just the total gravitational wave background, so that the total mean divided by the most important strain. So just like we had a most important mass that dominated your mass spectrum, you'll have a most important strain amplitude that dominates strain. So all of these curves correspond to different models, varying different parameters. This doesn't matter too much. It's just parameters of, say, the redshift, the mass ratio, the mass distribution, and so forth. But they're all peaked at some point. And one thing that we showed in this work is that you can change variables basically and rescale by this peak mass, such that you basically absorb most of your parameter dependencies. So all of these basically look the same once you do an appropriate change of variables. And so we've compressed things from this 3-dimensional distribution to a 1-dimensional distribution You can basically do this analytical expression. In terms of these rescaled variables, basically what you see happens is that as you decrease this characteristic number of sources, your distribution develops a larger tail. Your median falls below the mean. So all of these distributions have the same mean, which is this dotted curve over here, but they become less Gaussian with a larger tail as you decrease the typical number of sources that contribute to your background. And the impact of your discrete sources basically like I mentioned, is controlled by this characteristic number of sources. And this quantifies these features that I had mentioned before, right? The drop off of the median basically corresponds to this non-Gaussian behavior that I talked about before. And it's likely to be relevant within your observational band because it depends so strongly on the frequency. So you can compute with some twiddle math how this characteristic number of sources scales with frequency, and it scales very strongly with frequency to the minus 11/3. You can show. And so it's likely to cross an order 1 number within your band because it covers so many orders of magnitude. Basically, most reasonable astrophysical models will predict that this crosses some order 1 number within, say, a decade in frequency, which you observe. So this is likely to be important at some point in your frequency band. So we took this model, we implemented it, and we used it to reanalyze the nanograv data in this compressed parameter space. So blue here corresponds to the range of parameters that you need to fit the nanograv results. Red is what you would predict based on the scaling relations and mass function that I mentioned before, based on the direct observation of single supermassive black holes today. This discrepancy here is what I had mentioned before, and when I was talking about the amplitude. And okay, so this gap is the same as what I had talked about before. The dashed lines are lines of constant characteristic strain. So if you had only measured the amplitude of your gravitational wave background, this contour would be completely degenerate along this dashed line. But because there is these dotted lines over here are lines of constant characteristic number of sources. And because you don't detect the effect of these Poisson fluctuations in your data, you push this contour to the left, okay? So this upper left corner is more Gaussian, this bottom right corner is less Gaussian. And so there's already some information about the typical number of sources that are contributing to your gravitational wave background, which allows you to set constraints here on these parameters. Okay, so you can say in general, we show that there's a preference for models with a larger number of fainter sources. In our previous work, we had kind of speculated that it would be easier to miss some very rare tail. You know, if you wanted to make up your this like missing amount of gravitational waves by hiding black holes somewhere, we figured it might be easier to just have missed some small number of sources in this rare tail of your mass function. So maybe you actually lived somewhere over here instead of over here, so your peak mass was larger. But this seems to be excluded by this result. So you really need just like more fainter sources rather than few heavy ones. Okay, so I'll just finish with a few words on how this can improve and where this can go. In general, there's a sort of guaranteed improvement in pulsar arrays where you just continue looking at your pulsars for a longer amount of time. And this just continues to add to your signal to noise ratio. And it also lets you access lower and lower frequencies. You can continue, adding more pulsars and you can increase your SNR by looking at more and more pulsars. But one way in which this can improve faster is by new telescopes with a greater sensitivity, which is your noise, your noise term over here. So basically improving the denominator over here. And so you can improve higher frequencies faster by building new radio telescopes that have a better sensitivity. And this is currently the main limitation at higher frequencies. So you can improve those a little bit faster. This is just some examples of telescopes that have first light projected in the next couple of years. So SKA, and there's DSA 2000, which is supposed to have a quarter of its time dedicated to pulsar timing science, which will be a pretty important game changer in the field. And that's pretty exciting. And the idea is that if you improve your sensitivity, so these are some sensitivity curves for nanograv and 20-year data set, 15-year data set. And the idea is that you can improve these higher frequencies a bit faster with these new telescopes. And like I mentioned, these Poisson effects become more important at higher frequencies. So you have a larger probability of having one source that is brighter than everything else in these higher frequencies. So an example over here is some upward fluctuation where you just happen to live in a universe with a brighter source. These things are more likely to happen at higher frequencies. And one direction that the field is going in is, you've detected basically something that is a monopole. And, it'd be interesting to essentially resolve the sky in some way. So to be able to tell whether you're in a regime where you're dominated by one very bright source and resolve the sky. So this is showing, again, a map of your observed map of redshifts, essentially. This is in the case where you're dominated by one source and you have this pattern that I had shown before, or in a scenario where things are, one source does not stand out above the others, and it looks more like this. And you'd like to invert this and say something about the sources. So for example, localize an individual source or a map that is more, or a more stochastic background. But resolving this background is, I think, a really interesting direction in the field that the field is going in. So I'll leave you with my conclusions. PTAs opened this new window into the gravitational wave sky, and I think we should understand what produced the signal. There's a simple way to think about the gravitational wave background, and in particular, a simple upper limit to what it can be. Currently, it seems like the measurement is a bit above this, but it's still a bit tentative. And I think comparing our electromagnetic observations of supermassive black holes with the gravitational wave signatures can be very, very informative. So we'll leave you with that. Thanks.
Questions?
Thank you, a very nice talk. So I'm not super up to date with the literature on this, but I used to hear about this final parsec problem when you have two orbiting black holes and the orbital radius becomes less than a parsec, and essentially it takes infinitely long for these things to actually coalesce. I'm guessing the fact that we observed this data with the PTA suggests that this is not actually happening in the actual universe, but I guess one side of my question is, has this problem actually been resolved from the theory perspective? And relatedly, do you need to assume any of this for your modeling in terms of how long it actually takes for these things to coalesce?
Yeah. So for the first part of your question, I think one statement that one can make is that, measuring a gravitational wave background from in the nanohertz regime means that they do merge, right? So it does have to happen somehow. From the theory side, I haven't seen a lot of, using this data to then say something concrete about the mechanism. I mean, in the past, some work has shown that if you have like triaxial potentials, for example, these you need to refill the loss cone, and this can happen in triaxial potential. So there have been like solutions to the final parsec problem proposed, but then how, how do you constrain, how the details about how this happened, I think are something that are maybe a little bit lacking. So there are proposed solutions. Yeah. What was the second part of your question? How do I?
Any of these? in your
Yeah.
mind? Yeah.
So in my, I assume something very optimistic. So in the first part, this upper limit assumes that everything merges instantaneously. Yeah, just instantaneously. So it's like the most optimal, the most optimistic version of this. We also have some predictions in our paper that just assume some fixed time scale for things to merge. So if you say you have some redshift distribution for the latest merger, you can compute the redshift distribution of the past like n mergers by assuming some fixed time that it takes to merge. So we also do that, but you can always compute the most optimistic thing, which is just instantaneous.
So a related question. So is it possible to, with the PTA data set that we already have and with the data that's coming up in the future, is it possible to infer the distribution of orbital separations and the orbital timescales of these supermassive black hole binaries?
I think that would be very challenging to do in practice. I would be, I mean, where you're measuring, if you're only measuring, say if your entire data set is just the spectrum, if your entire data set is just a spectrum, I think there is just like too many knobs where it would be very challenging to actually infer that. I think it will always be degenerate with other things, and I think you can make educated guesses, particularly if there are some other aspects that can be constrained with other observations. But I would say it would definitely not be a clean inference. Yeah.
Thanks for a great talk. I had a question about this upper limit. Is binary eccentricity something you'd considered when setting this upper limit, and how would that affect what you found?
Yeah. So eccentricity, here we just assume circular binaries. The way that it affects your prediction is that it basically moves some of your emission from lower frequencies where you're now radiating in like all the harmonics of your orbital period, right? So it moves a little bit of power from lower frequencies to higher frequencies, but it's a very small effect. So there are works that do take this into account, and you basically need every single object to be like almost like 0.99 something for you to actually see a substantial difference in the spectrum that you predict. And so you move some of the power to higher frequencies, but then eventually everything circularizes anyways. So yeah, it tends to be a pretty minor effect in the spectrum. So it would be difficult, for example, right now, if you wanted to add this to your model and place constraints, it's very unconstrained, for example.
More questions? If not, then let's thank our speaker one more time.